Okay, Shira, the floor is yours.
Thanks very much. I hope you can see my screen well by now.
Yes.
Yes, okay. So many thanks, Ofer, for this very kind invitation. So my name is Shira. I lead the dynamical metrology group at the Weizmann Institute, where we mostly study extratropical weather systems. And I thought that talking to you, I should speak about the links between these weather systems and the planetary boundary layer, which is I guess it's the interface to what most people in this audience research. So I'd like to acknowledge my co-authors on this work here, Eyal Ilotovich, Oz Mendelssohn, Vered Silverman, and other members of my group at the Weizmann Institute, and also Sigalit Berkovich from the Biological Institute in Ness Ziona, and Virendra Gatte from Argonne National Lab. So I will highlight two of our recent works that touch on the link between extratropical weather systems and boundary layer characteristics. So the boundary layer, this is the bottom layer of the troposphere that is in contact with the surface of Earth. It is often turbulent and is capped by a statically stable layer of air or temperature inversion. And because of this separation between the boundary layer and the free troposphere, actually the study or the most of research of these atmospheric layers is done in isolation from each other. And this is very much justified. There are very different assumptions and approximations done at the boundary layer and also in the free troposphere. But actually, coming from the atmospheric dynamics field, which studies the free troposphere and atmospheric dynamics of the balanced flow in the free troposphere, we study high impact weather. And high impact weather basically affects us living in the boundary layer. And we've come to realize that many of these high impact aspects, whether temperature, winds, and others, they are not always translated to the surface in the same way. And this is, of course, obviously because of the boundary layer characteristics and the way it partly shields some of the influence from the free troposphere by this inversion layer. That changes, of course, from day to day, from region to region, and from regime to regime. So understanding the links between the boundary layer and the free troposphere, or dynamics in general in the troposphere, is very important for understanding these kinds of influence of high impact weather that we study in the group in general. And actually, our lack of understanding of some of these interactions between the boundary layer and the free troposphere across the inversion layer actually pose some of the biggest uncertainties in future projections of climate because we don't understand well enough the emergence of boundary layer clouds. So there's a lot of uncertainty stemming exactly from this process. In future projections of climate. So it's very important to study this kind of interaction, which combines very different tools, different communities, and, as I said, different assumptions. And this is actually not a new understanding. For a long time, people have studied boundary layer height, mainly motivated by the need to understand pollutant dispersion and concentrations in the boundary layer. So boundary layer characteristics in terms of temperature and humidity determine its stability and its vertical mixing and height. And for many years, these are references from Israel, already starting from Uri Dayan in 1988, who realized that the height of the boundary layer is very much and directly influenced by the governing weather systems in around the Eastern Mediterranean. So the boundary layer height, as you can see here, is lower under high pressure systems that govern the region and is much higher under winter low pressure systems or cyclones. And it also depends where, relative to the cyclone, we are actually located. Under the warm sector of the cyclone, the boundary layer is actually lower than under the cold sector of the cyclone, and I will come back to that. So these are mean heights of the boundary layer in Israel, around 1 kilometer or much higher in winter. But as you can see here in this plus minus standard deviation, is that there's also a lot of case-to-case variability. The variability of the boundary layer height varies a lot from day to day. And I'd like to actually address and speak about this variability today. Another mechanism that is very important to understand in this context is the actual mixing of air masses across this interface of the inversion, so between the free troposphere and the boundary layer itself. And there's a very nice review already in 1995 by Cotton et al. Reviewing how clouds and different cloud regimes act to ventilate the boundary layer towards the free troposphere, so from the boundary layer upwards. But there's practically no conceptualization of the other direction. So how the free tropospheric air mixes coherently into the boundary layer itself. So going from the other direction of dry air mixing into the moist boundary layer. So in the talk today, I'd like to address these 2 points. In the first part of the talk, I will discuss the variability of the boundary layer profiles in Israel in winter. And in the second part of the talk, I'd like to actually go deeper into the mechanism and ask how is air actually mixed into the boundary layer under the influence of cyclones, so the main weather system that we study in the group. So let's start from the first part. Here we focus on boundary layer profiles from Bet Dagan by using actual radiosonde data. Here you see the main profiles in winter. So the y-axis is the lowest 3 kilometers of the profiles, and you see different variables. So U and V, the east-west and north-south components of the wind, specific humidity, temperature, pressure, and pressure anomaly here in the bottom right. So pressure anomaly is the difference from this mean profile that you see here at each height. So all the gray points are the individual profiles. These are data for 12 years from Bet Dagan. And the black line marks the mean profile. You see that in the mean, we have more westerlies than easterlies. And also the wind speed increases with height as expected. Specific humidity and temperature decrease with height, and obviously also pressure. But the green lines also indicate the location of the plus minus 3 standard deviations. And you see that there's a lot of variability that actually spans this whole range within up to 3 standard deviations. So there's a lot of variability. So specifically the questions that we want to ask here are whether this variability can be actually grouped into regimes. So we ask, are there, and if they are, what are the dominant recurring regimes of boundary layer profiles? And we want to consider all of these variables together: temperature, humidity, wind, and pressure. And in the second step, we want to ask, well, is this variability linked to weather systems in the free troposphere? So are there links between the various boundary layer regimes that we may find and the regional synoptic scale patterns? And this work is now published in International Journal of Climatology and is mainly done by Sigalit Berkovic and also in collaboration with Oz Mendelssohn and Eyal Ilotovich. So how do we approach these questions? So as I said, we use directly the radiosonde data from Bet Dagan, lowest 3 kilometers with a high vertical resolution of 100 meters. We use daily data, so once a day at 12 UTC, for the winter months, December, January, and February, for the years 2007 to 2018. After some quality checks, we are left with 933 individual profiles of temperature, pressure, humidity, and wind, both direction and magnitude. And how do we classify this jungle of very different profiles and different variables? The method we use is a self-organizing map approach. This is a neural network-based algorithm that classifies data into groups based on their common patterns. And the way it does it, it takes all of these profiles and including all of these variables simultaneously, and it wants to reduce the variability in specific clusters compared to variability between clusters. And it does so in the end by reducing all the data into a 2D so-called map. And a map is basically an arrangement of clusters. In this case, it did so successfully in a 5x6 node dimension of a map. You will see in a minute what I mean. So there are different clusters. In the end, there are 30 different clusters of profile behavior that are linked to each other. And you'll see what I mean. This is why I wrote here that it's a continuous map. Okay, so after a successful classification of the profiles themselves, in the second step, we also want to examine the regional variability of these variables, such as temperature, pressure, and humidity and wind, and also geopotential and precipitation throughout the Eastern Mediterranean and the Middle East. And we do this by using global reanalysis data from the European Center for Medium Range Weather Forecast, ECMWF. The latest reanalysis, ERA 5, comes with a 0.5 degree horizontal resolution, or interpolated into this resolution. It has some higher resolution with 137 vertical model levels. Okay, so let me now illustrate what the actual classes look like. So what you see here is a self-organizing map. A 5x6 dimension map. So there are 30 different clusters. So each of these boxes now shows the resulting mean wind of that cluster. So the arrow here is horizontal wind. It means that this kind of arrow is southwesterly wind. That is very high, so very strong. It shows the profile in the lowest 3 kilometers. This is the y-axis, and this is the magnitude of the wind shown by the arrow. Now, the nice thing about this algorithm is that each individual profile out of the 933 is attributed to a single class. This means now that each of these classes covers somewhere between 2.5 to 4% of the profiles, of the individual profiles. And what you can see straight away is that they're very different from one another. So the successful classification actually managed to distinguish between very different profiles. In some cases, we see that there is a main profile of very strong westerlies in all of these right side of the map. Strong westerlies, they can be south westerlies in the upper right corner or north westerlies in the lower right corner. Of course, it increases very much with height. In the other side of the map, there are also rather strong easterlies on this left side of the map, and also here in the middle in these classes right here. And in all of these areas of the SOM map, you see that there's also very strong wind shear. So wind changes very much with height. And a characteristic of this SOM algorithm is that adjacent classes are quite similar to each other. This is why it's a continuous map. Even though individual profiles are attributed to a single cluster, there's still a continuum of regimes. This also means that if you look at very different edges of the map, they will be most different. And indeed, this is what we see. So strong southwesterlies are very different from these regimes in the opposite corner of the map. So very different regimes will be found further away on this map. So, okay, I spent quite a lot of time explaining this, but from now on, I will show many plots that look like this, showing 30 classes, and each class will be the same, would have the same group of profiles in it. So class number 1 will always have the same profiles in it. And here I only show the wind, but what about the other variables? So here we also see at the same time specific humidity, temperature, and pressure anomaly. And I remind you that the classification is done simultaneously on all variables together. So the regime with the easterlies here has this temperature, humidity, and pressure profile. So this is a lot to grasp at first sight. Specific humidity is shown in red, and the axis is here in the bottom. Of course, it decreases with height. Temperature as well is shown by the blue axis here, and pressure anomaly by the green lines. Okay, so there's a lot of information here, but what you could see is that the classification is actually successful in the sense that very different structures, very different profiles are found at the edges of the map. So on this left side of the map, you see the driest profiles shown by the red line here. The humidity also drops. It's dry to start with, and it drops even further very sharply. But it's also the warmest profile. On the other edge of the map, humidity is quite high and temperature is the lowest. And if you look at the pressure anomaly in this right side is negative compared to the mean for each height. But on the other side, it's the highest, and it even increases with height. So these are very different behavior found at different areas of the map. But you can see that also the classification did very well in also capturing not only the absolute value of these fields, but also the shape of the profile. This is how it operates. So you can see that sometimes specific humidity, for example, drops rather linearly, such as this in node number 16. In others, as I said, it drops more sharply, but in other cases, it has this kind of S shape to its decrease with height. Pressure anomaly also behaves quite differently. Sometimes it's rather the same at each height. Sometimes it's very much height dependent. And the same goes for temperature. So, of course, a very important variable that I already mentioned is the boundary layer height that is calculated based on these fields. So here is the boundary layer height calculated with a bulk Richardson number. And you can see that this dry, warm, high pressure regime is characterized by the lowest boundary layer height, whereas the highest boundary layer height is found under these deep negative pressure anomaly, cold, humid regimes. And there are many others in between. I'd like to mention that even though we have a lot of variability between the clusters, there's still a lot of variability also within clusters, at least considering boundary layer height. But the algorithm does not classify by this variable. It classifies by the whole shape. So some profiles can have a similar shape. That's why they're found in the same cluster. But as you can see, for example, in this node, number 10, that has 29 members in it, you see that the histogram of boundary layer height is quite wide still. So there's still a lot of variability within classes. So now let's look at the regional patterns. Are some of these variabilities actually attributed to regional variations? So the first thing we look at is sea level pressure. So these are now actual geographical maps. I hope you can recognize the coastline. It spans from Greece and the Balkan countries to the Black Sea here, and the Red Sea extends right here. I hope you can see Bedagan is right in the middle. And these are maps, so average maps, composite maps of sea level pressure in hectopascals, average for all the members of each class. What you can see straight away is that the patterns are very distinct and very different from each other, and also very much dynamically meaningful. So sometimes in these regimes, as maybe you could already guess, we have deep Cyprus lows, so deep Mediterranean cyclones as you can see here, but a relatively low pressure. And it's deepest in this corner here, but all of these groups are characterized by such deep winter cyclones. On the other hand, this left column in the map is characterized by the winter highs. And these high pressure systems can appear on average in different locations relative to Bet Dagan. And obviously this very much affects the boundary layer profile. So the position of this high pressure system, it affects the resulting actual profile at this particular point here in Bet Dagan. There are many other things that you can see here. There's a Red Sea trough that you can see in most of these regions. In some of these groups, it actually extends all the way to us, such as in this group. And there are also some groups that I marked here in green that are characterized by very low surface, so sea level pressure gradients in our area. And this information is complemented by what happens in the middle troposphere. So here is the regional composites of the 500 hectopascal geopotential height in meters. These are basically the pressure systems at a height of about 5.5 kilometers, so above the boundary layer and above the height which we actually classified. And also here you see very coherent structures. So we have low geopotential, so trough systems that extend from the north towards the Middle East in these deep winter cyclone regimes. And we have winter highs. Under the winter highs at the surface, we also have ridges in the middle troposphere that extends from the south, especially in this regime. We also have more shallow trough systems that extend towards the Middle East. This is in the Red Sea trough regime. This means that these regimes are actually active Red Sea trough regimes that can produce precipitation. And these more moderate pressure systems are actually caused at the surface by Red Sea trough to the east and some high to the west of Israel, but the shallow gradients are actually caused because there's no significant system in the upper troposphere or middle and upper troposphere. Okay, so this was the actual weather systems, but what about the temperature patterns? We saw that there are very different temperature behavior at Bet Dagan, but are there actually regional variations? And the answer is a strong yes. These are, what you can see in these maps is that these temperature anomalies extend very much throughout the Middle East. So these are temperature anomalies at the height of about 1.5 kilometers, the 850 hectopascals geopotential layer. You see these very strong cold anomalies at this height that extends over the Eastern Mediterranean under deep flows. And very interestingly, under the high pressure systems, we have sometimes warm temperature anomalies or extremely warm temperature anomalies, such as in this group, but sometimes a cold temperature anomaly under winter high conditions. Actually, the center of this anomaly is further to the southeast of us. Okay, so as you can imagine, there are also regional anomalies in humidity and other variables that I don't have time to show here. We have it in the paper, but what is interesting to show is that there are also regional precipitation anomalies that you can actually highlight using this kind of classification of a single point in Bet Dagan. So this is interesting that under deep high, actually, we have very consistent and coherent anomalies in precipitation. So not anomalies, actual precipitation accumulated over 12 hours around the time of the radiosonde launch. And you can see that there is a lot of precipitation in Turkey in this regime, but more over the Syrian and Lebanese and Israeli coasts in these two regimes, over Cyprus in this regime. And the green line actually encircles areas that are statistically significant. We did some special kind of testing. Of course, there's absolutely no precipitation under the winter highs, whether warm or cold. But I think what is nice to show here is that under the active Red Sea trough regime, you see very significant precipitation, especially under this node 16. So there's, despite the rather shallow trough that we saw, there's a lot of precipitation that extends in these otherwise very dry regions. So I already come to the summary of the first part of the talk. We saw that there are 4 major synoptic groups that dominate the boundary layer profile variability in winter in Israel. The first is the deep winter lows. They have strong southwesterly to northwesterly winds, high boundary layer height and precipitation, also cold anomalies. Strong winter highs in the Red Sea trough have also an upper southerly ridge extending from the south, moderate easterly winds up to 1 to 2 kilometers, and a strong wind direction shear. They also include hot and dry extremes, but also sometimes cold temperature anomalies. There's another large group of moderate pressure gradients under shallow lows, high to the west and Red Sea trough to the east of Israel, but no significant systems in the upper troposphere. And quite uniquely, we also found an active Red Sea trough group or groups. These are accompanied, the Red Sea trough that is also accompanied by upper northern trough that leads to enhanced upward motion and unstable conditions, heavy precipitation throughout the region. And this is important because this is a first objective classification of an active Red Sea trough. And in general now, we saw that there are distinct categories of thermal stability, boundary layer height, and also turbulence that we have more details about that in the paper. So yes, there are recurrent regimes and they are tightly connected to the synoptic conditions. And I'd like to highlight the quite amazing aspect. We were quite surprised to see that a classification of a single profile from a single station point in Bet Dagan is actually able to discriminate between synoptic regimes in such a sensitive manner that we're even able to identify the active Red Sea trough that is a long-standing challenge in the region. All right, so now I'd like to go further into the second part of my talk and go deeper into understanding extratropical cyclones and how they influence the boundary layer. And we specifically now take a Lagrangian approach by following actual air masses that are associated with the circulation around cyclones and see how they interact with the boundary layer. And for this, I take the example of the dry intrusions, and I will say exactly what this is now. So an extratropical cyclone is not a symmetric feature. It's highly antisymmetric, as you can see in this picture over the UK of the cloud structure around the cyclone. And this is because the flow around the cyclone is very much not symmetric outside of the tropics. So what we typically have, this is very complicated, I only go over it very briefly, but we have many types of cyclone relative motions of air at different heights of the atmosphere. I'd like to focus on 2 of these aspects. So this is the center of the low pressure system of the cyclone. We have typically the warm front extending here and a cold front here that separates the warm and moist from the cold and dry air masses. And what we usually see is a strongly ascending air mass that is called the warm conveyor belt in the warm sector of the cyclone, and a dry intrusion air mass that is a strongly descending air mass in the cold sector of the cyclone behind the cold front. And this ascent and descent are not convective motion. They're not directly upwards or downwards vertically, but they are slantwise motion. So this motion extends over more than 1,000 kilometers on the synoptic scale, but it's slantwise ascending in the warm conveyor belt and it's slantwise descending in the dry intrusion airstream. And I would focus on the dry intrusion airstream. So looking now in 3 dimensions at the cyclone environment, here you see, I hope you can see this, these lines indicate sea level pressure, and this is a local minimum of sea level pressure, so a low or cyclone center right here. It has the warm front extending from it and the cold trailing front that extends southwards. And now looking in 3 dimensions at the flow around it of the dry intrusion, we see that these arrows represent such flow of air masses from the upper troposphere downwards, slantwise, towards the equator on this side, towards the cyclone on this side, and they fan out behind the cold front. So this is a dry intrusion airstream that is very interesting now in the context of the interaction between the free troposphere and the boundary layer, because as you can see, it actually cuts through potentially. So this air starts from the mid-latitude jet, and it descends potentially all the way towards the surface. It does so especially near this anticyclone here, the high pressure system, but also closer to the cyclone center. Then now the question is, how low does this air actually go? So I said that this air descends, and I think many of us are used to thinking about subsidence or descent of air together with warming. Of course, when air descends, it warms up adiabatically very strongly, and it therefore creates a strong inversion above the boundary layer. In other words, it disconnects from the boundary layer. But I couldn't stress it even more. The slantwise nature of this descent makes the whole difference. This is not a convective motion downwards. This is not local vertical subsidence, but this is slantwise descent. And this slantwise descent means that the whole picture can be actually different. And actually, this is what we ask. We ask, does this dry intrusion air enter at all the boundary layer? Or does it actually create a stronger inversion, a stronger separation between the free troposphere and the boundary layer? How do the boundary layer, how do dry intrusions interact with the boundary layer, and how do they influence the boundary layer structure in terms of temperature, humidity, its height and inversion properties, but also clouds? I remind you that the boundary layer clouds have a lot of uncertainty. And finally, do dry intrusions impact the actual surface? And if so, how? And this work is summarized in this paper that is now published in Journal of Geophysical Research, Atmospheres. Some of you may have heard some of this work in the talk that Eyal Elotovich gave. Okay, so let me just give you an example of what such a dry intrusion can actually do. So this is a water vapor channel image above the UK showing a dry air intrusion here in the dark. So the darker it is, the less water vapor there are in the troposphere. And here you can see an evolution of this dry intrusion that actually propagates over Central Europe towards the Mediterranean. And it creates this nice cold front structure. So it extends behind the cold front, as I said earlier. And you see the damage that was caused in Europe during that evening. So wind gust measurements, this is from Zurich, reached 100 kilometers per hour during this time. And there was a lot of wind damage reported in all of this area where the dry intrusion actually passed through. So it seems that there is a connection between this type of air that descends from the mid-latitude jet towards the surface. But let's see, how do we approach studying this kind of phenomenon in the group? So we take, as I said, the Lagrangian approach. We want to follow these dry air streams as they descend towards the surface around the cyclone. And we do this again by using reanalysis data, so global reanalysis data, error interim in this case, for almost 40 years. And we calculate air mass trajectories using this Lagrange code. And we calculate them systematically forward in time in 3 dimensions using some given starting intervals. and we apply a Lagrangian definition of dry intrusions requiring that they descend at least 400 hectopascals. This is about half of the troposphere in 48 hours. And now applying this threshold on all of these calculated trajectories, we end up with things like this. So what do we see here? Here we see each line is colored with pressure. Each line represents an air mass trajectory. And the pressure it is colored with represents its height. So for example, here you see a coherent set of such trajectories for the same date of the satellite animation that I just showed. It shows that air masses descend from the upper troposphere, a height of about 10 kilometers or 200 hectopascals, from around Greenland, over Iceland, the UK, Western and Central Europe, towards the Mediterranean and North Africa, where they extend in this way. Some of these trajectories or air masses ascend back up. And there's a cyclone that is found right here in the Mediterranean in this case. So we have these data that we can then analyze. And this is just one example of a single event, but we do this for 40 years of data, as I said, and now we have a climatology of this phenomenon of dry intrusions. So this is the winter climatology of dry intrusion outflows. These are the lower portion of these trajectories. So sorry, I only take this part that can potentially interact with the boundary layer when it's found in a pressure of 700 hectopascals or higher. So all of these green portions. So this is the climatology of these green portion of dry intrusions that can potentially interact with the boundary layer in winter. And you see that they are mostly found above the oceans, but also at some significant percent of the time, they can also occur in our region and overland. And this is for the Southern Hemisphere, winter, June, July, and August. And this is for December, January, February in the Northern Hemisphere. So this phenomenon peaks in winter. And previous work showed that the occurrence of dry intrusion is actually associated with very much increased boundary layer height. In the majority of the cases, in over 75% of the cases, dry intrusions are associated with increased boundary layer height. And we'd like to now study this in more detail. So we focus on a specific region here in the Azores Islands, where we have about 6% of the time in winter, we have the occurrence of dry intrusion. So we can contrast this behavior under these situations to other times. And we focus on this region also because it has a measurement site of the US Department of Energy, the ARM site in the Azores, that is equipped with standard meteorological parameters, but also with a cloud radar and a laser ceilometer that we can observe the boundary layer with. So let me give you an example of one of these events that hit the region. So the Azores Island is found here in this X, and these are dry intrusion trajectories that arrive at this site at the end of December 2017. And the color of these trajectories is the pressure, as I said. The more yellow it is, the lower it is. So it actually descends from the upper troposphere in the Western Atlantic towards the Azores. And now what happens during this time? So this is now a complicated plot, but I will walk you through it. So in the bottom panel, you see height time cross-section during these days. So the x-axis is from 28th of December, and it extends to the 1st of January, 2018. And this is now height from 1,000 hectopascal at the surface to 500 hectopascals, about a height of about 5.5 kilometers. And the shading is specific humidity. Potential temperature is shown in the black contours, and equivalent potential temperature is shown in the red contours, and equivalent potential temperature is shown in the black contours, and the boundary layer height is shown by this blue line. Now,
where is the event itself? These are the actual dots. So the dots that are shown here are the dry intrusion trajectories that hit this region. So this is a time height cross section at this region in the Azores, right? So around the 30th of December, we have the first arrival of these trajectories that arrive at the region at a height of about 800 hectopascals. In the next time step, after 6 hours, we have a clear dominance of these air masses throughout this atmospheric column. And later, it even penetrates deeper, almost to the surface, until it ends on the 1st of January. And what you can see is that during this day, or a bit more than a day, we have a significant drying. And the drying actually penetrates all the way to the surface. See that if you only look at the surface, we have this very significant drying that occurs on the 30th of January, such that at the peak of the dry intrusion event, we have very low specific humidity, and this is a marine environment. This is very not common for the region. Later on, we have a recovery from this dry conditions. We also have cooling at the same time. You see it with the temperature contours. So there's also very significant cooling, not only drying during this event. And this, of course, doesn't only occur at the surface, but it actually starts from the middle troposphere or from the upper troposphere. See how this actually dry air penetrates from the middle troposphere in this region towards the surface. But of course, these air masses actually originated further upstream in the upper troposphere. Okay, so we can see that it has some significant effect, but let's now look specifically at the boundary layer. So what we did in this study, we had data for 3 winters, for 3 years, for the winter months, December, January, and February. And we actually divided all the timings of to different categories. So dry intrusions dominated the region about 6% of the time. There were 31 events during this period. And we also categorized the other times into times that are beyond dry intrusion, so after dry intrusion passed the region, and also times we use for the categorization that is not accompanied by a dry intrusion. So we do the same for all of the 3 years. And what you can see is that here we have average maps of sea level pressure fields during these different categories of times. You see the Azores Island in this X, and this area covers now the whole of the North Atlantic. I hope you can see the Iberian Peninsula, for example, here, and this is Newfoundland in this corner. And you see that climatologically speaking, looking at these categories, we have the Azores high pressure system dominating the region. But when dry intrusion dominate, the moisture. So here using the same colors, dry intrusion in red, and the other categories in these same colors, we can look at the vertical profile of specific humidity, which shows that it is the driest of all during dry intrusions, obviously, as expected. It also remains dry 24 hours later, using in blue, like you see here in blue, and it's very different compared to the other times. Now, when you look at relative humidity, actually what is interesting is that during dry intrusions, just below the boundary layer top, you see that during dry intrusions, the relative humidity is actually highest during this time. And this is, of course, because of temperature. So looking also at the temperature here in this, on the left side here,
you see the temperature is also lowest during dry intrusion. This is why relative humidity is actually the highest at this time. So this is very interesting because it affects the clouds, as you will see in a minute. You can also see the vertical mixing within the boundary layer as it is manifested in the potential temperature profile. You see that it's almost constant with height during dry intrusions, and also the highest. Yes, and what you can also see is that during dry intrusions, there's a very strong signature of an inversion. So probably an inversion layer changes very much in response to the presence of dry intrusions. But these are all averaged profiles, and you can see the variability in this shading. And of course, it's quite dangerous to infer individual profile properties from these mean conditions. So what we did is we looked at the individual profiles and we characterized the inversion properties. And this is what you see here. So we characterized the inversion base for the different dynamical categories. And you see that during dry intrusions in red, the inversion base is indeed highest. This is basically the information binned into different inversion base bins. Now, what about the inversion strength? You can measure the inversion strength using the difference of specific humidity, like you see in this panel B, or difference of temperature. Using both aspects, you see that during dry intrusions, there's a long tail towards high values, especially when you compare it to the climatological conditions when dry intrusions are not present in the region in gray and black. So usually inversion strength has this particular difference across the inversion of temperature, let's say up to 2.5 temperature difference, but during dry intrusions in red, they peak in much higher inversion strength in terms of temperature, but also in terms of specific humidity. This is even higher in the post-DI stage. And the inversion depth itself in meters is also highest during dry intrusions in red compared to all other times that peak in much lower inversion depth itself. So both the base is lower and the depth is thinner. Okay, so we see that during dry intrusions, the inversion changes very much. It becomes thicker, stronger, but also higher. So there's more, so the actual elevation of the boundary layer changes. And this is another thing we looked at using the individual profiles. And there are many ways to quantify the boundary layer height. We did this using 5 different methods based on the radius-on data, and the methods are detailed in this paper. And we also looked at the boundary layer height using the oscillometer at the site for all different categories again. So dry intrusions in red. You see that whatever method you choose, basically we all know that there's a lot of variability among the different methods, but whatever method you choose, the boundary layer height is actually highest during dry intrusions compared to all other dynamical categories. And this remains relatively high also in the next 24 hours in the post-DI stage. So we can say until now that dry intrusions induce a cold and dry anomaly together with a stronger, higher and deeper inversion. And now I think because of the lack of time, I will skip the next section in which we looked at the actual surface fluxes, but they also modulate the surface fluxes from the ocean very much. So I'd like to now put it all together and look at a similar plot as we saw before, but now it's averaged for 31 events, not just the one example that I showed in the beginning. So again, a time height cross-section from the Azores island, showing specific humidity in the background relative to the timing of the first arrival of the dry intrusion, which is relative time 0 right here in the center. You can see that this profile in the boundary layer and above it is very much modified by the arrival of the dry intrusions. And these dots here represents the maximum pressure which the dry intrusions reach for each event. So now each dot is an event, not a single trajectory. And you can see that they actually reach into the boundary layer, so deeply into the boundary layer. They're mixed into the boundary layer. They are drier and colder. This is how they get in because of these unstable conditions. You can see this unstable, potentially unstable conditions when you look at theta E, the equivalent potential temperature. There's a local minimum here during the time of the dry intrusions, which means that if you look locally, vertically, there's a negative potential temperature, equivalent potential temperature gradient with height, meaning that it's potentially unstable. So these unstable conditions allow the mixing of this dry and cold air into the boundary layer. Okay, so finally, I'd like to mention now the effect on clouds. Obviously, humidity, temperature, and stability profiles are the building blocks of how clouds are formed and sustained. And our way to look at these quantities using radar data is often done using such plots. So these are the reflectivities, radar reflectivities in different ranges with height. So this range between 0 and 20 dBz means that it is actual raindrops. Lower than that, that's drizzle. And lower than -20, this is actual cloud droplets. And under no dry intrusion conditions, no cold front conditions, we see actually a maximum of cloudiness below 1 kilometer height, and almost no rain. But if you look at the other categories, it changes very much. So if we focus here on the front passage here in the yellow in this panel, you see that there's a lot of rain in the front passage and very different cloud distribution. Now, right after the cold front, when the dry air dominates, we see something also very different from the climatology. So we still see a little bit of rain at the middle troposphere, which you don't see already at the lower levels. Probably most of it evaporates as it drops. And the clouds are also different. So the droplets are bigger. You can see that the reflectivities increase, and they also occur at a higher elevation. This is in accordance with the higher boundary layer height. And a lot of it is sustained also in the next 24 hours. So, yes, I think I said what I wanted to say here. Yes, another thing is that you see this void when the dry intrusions dominate the region. There's practically no reflectivities at all in this middle troposphere due to the dry air. But in the boundary layer, we see a lot of modification. So there's even more clouds than before, despite this dry air mass. And this is because of the strong surface fluxes, which are also added to the party, and I didn't have time to show how they change. So to summarize this part of the talk, we actually looked deeper into the circulation around the cyclone, and specifically the dry side of the cyclone, which can potentially interact very strongly with the boundary layer. And during these times, using the example of the Azores Island, we showed that during these events, we have an interaction that is mixed as a top-down and bottom-up interaction. What I mean is that first, the deepening process of the boundary layer starts top-down by the DI air mass itself. First, it mixes into the boundary layer. It creates potential instability due to the incoming low theta E air. So the air that is incoming is both colder and drier than the in situ boundary layer air. There's stronger, deeper, and more elevated inversion due to this entrainment of the cold air mass. And please be aware that this is very different from subsidence that creates a relatively warm air mass on top of the boundary layer. This time, this descending air creates a cold air mass that penetrates into the boundary layer and creates the different inversion properties. This drying, cooling creates also stronger wind gusts, which I didn't show now. And all of these together very much trigger very strong surface fluxes, both sensible heat fluxes and latent heat fluxes, so ocean evaporation. And this actually enhances the vertical mixing now bottom up. So this work is now summarized in this publication. And I'd be very happy to discuss, hear your questions, and I'd like to say that in the group we look mainly at dynamical systems or weather systems, and these are just two aspects that touch on the boundary layer, but we also look at monsoon dynamics and dynamics of wildfires in Australia and dust storms, and more closely into dynamics of weather systems in a more pure way. So thank you very much for your attention.
Thank you very much, Shira. I'd like to open the floor for questions and comments.
Perhaps I stop share so I can see you. Okay.
Hi, Shira, can I ask?
Hi. Sure.
So I have two questions about the self-organizing maps. One is about the number of categories that you choose, why you chose that, and can you say something about that?
Sure.
And there's another question about the PBL height. You said that you have a high variability in each category, and I was wondering whether the daily cycle may be relevant in there.
Great. So let's start with the first question, the number of categories. This is a very good question because it is up to us when we use this algorithm. This is something that we can choose. We tried many different configurations. We were sort of aiming to find as little as possible at first, but nature is different from what we want it to be. It's not so clean. So we experimented with both very low number of nodes or classes and also much higher number of nodes or classes, and we wanted to see how well they are separated. So too little classes actually it was just hiding too much of the variability that we were interested in. So it put all the highs together without differentiating between the cold and the warm ones. And it showed a lot of sort of medium, not interesting configurations that are not really meaningful to us. So too less it wasn't very good. And we also tried many more. And we tried to look in between what kind of categories we get. And when we moved from many more categories to 30, we realized that above 30, we start to have some repetition of classes. But going also from below 30, we missed some of the nice active Red Sea trough classes, which were quite delicate. So already when going to 4x6 or 5x5, we didn't see the active Red Sea trough group. So it was quite a sensitive one. And we didn't want to miss that. And I think beyond 30 is already too much. So we stayed with 30 in the end. And okay, so your second question was, can you remind me? I forgot.
About the PBL height variability in each of the categories, whether sub-daily cycle may influence their...
Yes, so of course it influences the boundary layer height. This is one of the reasons why we chose to work with profiles at the same time. So they were all done at 12 UTC. Yes. For the other part of the talk, we analyzed all radiosondes together from all times. Also, they were available more than twice a day. And we realized actually that the differences, because this is a marine environment, were mostly in the lowermost a few hundreds of meters. So this didn't matter so much for the other study. But for Beta Gun, we only used the 12 UTC ones. So we were blind to the daily cycle.
Thanks for the interesting talk.
Thank you.
Okay, we're running a bit over the 1 hour for the seminar, but if anyone has any other question, please go ahead. Okay, in that case, Shira, thanks again.
Thank you.
And,
so it was my pleasure. And if you feel like you can always write me, and I'm here not so far from you. So